Hi, I am Atish Mazumdar. I am a retired professor of physics, now an online tutor. This is my email address, and below that is my mobile number. I live in New Delhi, India. If you are calling from any other country, please take care of the time difference. Thank you. Let us solve the second problem in the series of electrostatic equilibrium of charges. Let us assume that there are four charges of equal magnitude and of equal sign kept at four corners of a square, and we have to find the charge which will have to be kept at the center of the square in order to have all these charges in equilibrium. That means all these charges, the net force on all these charges to be equal to zero. Let us first analyze the situation. Let us concentrate our attention on the charge which is at the right hand upper corner of the square, and let us see what are the forces acting on this charge. The first force is due to this charge. I name these corners. This corner I name 1, this corner is named 2, this is 3, and this is 4, and the center I name it as 5. Now the charge 1 uh, will be experiencing a force due to charge at 2, and this force will be towards right. So this is the F1 force. Similarly, the force on this charge due to Q at 4 will be vertically upwards, which I have named as F2. Now the resultant, if we can find out the resultant of these two forces by parallelogram law, and that will be along the diagonal of this square, and this will be the resultant. And in addition to that, there would be a force due to Q3 which will be along this diagonal, and that I have named it as F3. So total of all these three forces will be along this line. Now for the charge at 5, which is at the center of the square, will also exert a force on the charge that is at 1, and that will be directed uh, along this arrow of this diagonal, and therefore if F4 this force F4 is equal to F total of F3 and Fr, then this particle which is at 1 will be in equilibrium. And similarly the situation for all these charges at the corner. And because all these charges are of same magnitude and they are equidistant from the charge at the center, so the force that this charge will exert on minus q dash at the center uh, would cancel the force that is due to Q3, and similarly the force due to Q2 will be cancelled by the force due to Q4. So therefore this particle will also be at rest. So therefore the whole system will be equilibrium, can be in equilibrium if we choose the proper value of the charge at the center. Let us equate the forces, that is on the charge Q at which is at 1, and we get Fr plus F3 should be equal to F4, because these forces are equal and opposite, and we have dropped the negative sign as before. That is much more convenient to solve this equation without the sign, and afterwards we can put the sign if it is required. So the force Fr has to be found by vector sum of F1 and F2, and that is the magnitude of which is square of f1 plus square of f2. Fr is equal to square root of k into q divided by a square whole square plus k into q divided by a square whole square, because these two charges are exactly equal in magnitude, and wherefrom we get Fr is equal to square root of 2 into k into q divided by a square. So Fr plus F3 we obtain by adding the force F3, which is k into q square divided by square root 2a, is the distance between the third charge and the first charge. So that will give me k into q square divided by a square into 1.914. Now F4 we can calculate using the Coulomb's law again, and that will be k into q dash divided by square root 2 into a divided by 2, because this will be the half the diagonal. This is the half the diagonal, therefore it has to be divided by 2. Then F4 will be equal to 2 into k q into q dash divided by a square. So we can equate the right hand side of equation 1 and 2, and finally we get q dash is equal to 0.957 into q.